I made this line following robot that learned to drive perfectly all by itself. I gave it 0 instructions myself. No if statements, no rules, nothing. But I did it in simulation though. Cause real hardware is a nightmare. Wires get loose, sensors fail. Who wants that headache? In this project, I used Gymnasium to build the environment, Pygame to frame the visuals, and PyTorch to train the models. This simple rectangle represents our robot, and the red line marks the forward direction. To detect the path, it has this array of sensors. When a sensor is over a black pixel, it turns on, and when it is over a white one, it remains off. This gives the robot a basic digital snapshot of the line below it. This green circle is its hitbox, which brings us to a very important problem. How do I reward the robot for staying on the track? How do I tell the computer what on the track means? The simplest idea I had was to just scatter coins along the path. The robot doesn't see coins, it just sees sensor values. When the green hitbox hits the coins sequentially, we reward it. Because the coins are scattered only on the road, the robot learns that when it sticks to the road and moves fast, it gets more rewards. Finally, how does the robot actually move? It uses a classic method called a differential drive. To understand how it works, imagine a robot turning over a tiny slice of time. Its two wheels trace out concentric arcs. L is the distance between the wheels, R is the turning radius to the inner wheel, and delta theta is the angle the robot turns through. Let's assume that in a tiny time interval delta t, the left and right wheels travel distances of delta LL and delta LR. First, let us find the change in angle delta theta. We start with the basic formula for the length of an arc, S equal to R theta. Applying this to the sector COD gives this equation, and sector AOB gives this equation. After a quick rearrangement and substitution, we get our relation of delta theta in terms of the known quantities. Next, we need to find the change in position of the center of the car, which is equal to the length of this highlighted curve. Using the same S equal to R theta and the previous relations, we see that the required distance is just the average of the distances travelled by the two wheels. By the way, all these calculations are done assuming all the delta terms are small, and the actual integration follows Euler integration rules. For my first attempt, I decided to keep the robot's choices as simple as possible. At any given moment, it can only pick from one of three predefined actions. To make a turn, one wheel moves forward while the other stops moving. To go straight, both wheels move forward together. I just choose a maximum speed of 3 for each wheel. The plan was to teach a model the best action to take for any given state, where the state is just the on-off values from the robot sensors. I used 12 sensors in total, arranged in 3 rows of 4. The model is a simple multi-layer perceptron with a single hidden layer of 32 neurons. It has 12 input neurons for the 12 sensors and 3 output neurons, one for each possible action. To train this, I used the DQN algorithm. The basic idea is that the network takes the sensor values as input and its 3 output neurons predict a Q value for each corresponding action. You can think of a Q value as a score that predicts how good an action is in the current situation. More formally, it's the expected future reward of taking that action from this state. So the robot takes in the sensor readings, the network outputs 3 scores corresponding to the 3 possible actions, and we can just perform the action that got the highest score. Great, so let us now see how it goes. At episode 60, it first starts learning. And immediately, maybe it randomly had seen more examples of the black tracks, it starts performing particularly good in the black tracks and worse in all other tracks. Then by episode 80, it tries to also focus on the other types of tracks. The black counterclockwise starts getting better by episode 160, but again slacks off by 240. Alright, so in this gap, let me quickly explain how I did the tracks and the coins. I designed the tracks in Inkscape as SVGs. The cool thing about SVG is they naturally store the vector coordinates, basically all the waypoints for the line. So I wrote a Python script which takes in the SVG as input, and first it makes the PNG for the sensors to see. But more importantly, the waypoints are used as coins along the path. Sometimes when I feel there are too many coins, I can also take like every 10th waypoint as a coin or something. Anyway, the next commentary is coming up. After that I will tell you all about the other tracks I tried and how that went. Next, by episode 280, the black clockwise becomes rock solid on the track. The black counterclockwise also gets pretty stable by episode 320. Then by episode 350, the white counterclockwise slowly starts sticking to the track and stabilizes by episode 400. Alright, so as planned, let me tell you about the different tracks I tried. I started simple. The first one was just an oval track and then a hexagon. The agent learned these with no problem at all. It even handled easily the augmentations you had already seen, like going clockwise and counterclockwise, the track colors inverting, etc. In fact, these simple tracks learned with far fewer than 32 hidden neurons. They were just too easy. So I moved to this rounded square track, which is the one you are watching right now. This is where things got really interesting. Without the color inversion, it learned okay. But as soon as I turned that on, it got completely confused. It actually took all 32 neurons in that hidden layer for the model to finally get a grip. I also had made a sharp 90-degree square track. The model with the current actions was not being able to learn that at all. I also made another split track version of these tracks, half black path on white and half white path on black. Even on the oval split track, the model failed miserably. The agent couldn't learn that at all. It was just too confusing for it. Now back to the commentary. In the middle, the black counterclockwise sometimes got bad, but again went up fine. And by episode 600, all of them got quite stable on the track. We trained them till 800 episodes and ended the training there. So that is the project till now. The code for everything you saw is on my GitHub. I have put the link in the description. This is my first video and I am still learning. I'd really love to hear what you think about the video was. And if you have any questions, just drop them in the comments. I will do my best to answer. We know the agent failed on the square track with the current setup. But next we will see exactly what tweaks we can do to this version to make those sharp turns work. We will also start exploring situations where the action space is continuous instead of just choosing one of the three options. So stay tuned. Thanks for watching. I will see you on the next video. Bye bye.